Welcome to Physical Attacks and Countermeasures, the fifth session. We will see the basics of power analysis attacks. At the moment, we don't deal with the attacks at all in this session. We just deal with the power consumption characteristics of let's say, electronic devices. What are the power analysis attacks? Actually, they are considered as the most powerful certain analysis attacks. No? If we compare it to, for example, timing attacks that you have seen before, because in timing attacks, you usually are able to measure the entire time, or let's say the time of the entire encryption. But now here with power analysis, you will be able to get some information for every clock cycle. Now, what the device is doing. Of course, not exactly what the device is doing, depending on the adversary model and depending on the attack, but you get much more information compared to timing attacks. And usually these attacks, the power analysis attacks, are able to break any implementation by observing their power consumption. We will talk about this instantaneous power consumption later. And when this instantaneous power consumption is measured during the computation or operation of the cryptographic algorithm. Now, of course, if we say any implementation, it means that the implementation does not have any countermeasure or any measure to defeat these kind of attacks. It means that the implementations that they are not protected against these kind of attacks. And if you consider some kind of countermeasure, then of course the attacks will be harder, and then it will not be trivial to perform the attack. One thing that you should consider, and I explained it a couple of times, that in almost every attack against cryptographic systems or cryptographic implementations, there is no device that you can put a finger on it and say, this is secure. Under which adversary model you define the security. This is important. Means that if you even consider countermeasures, these countermeasures are able to provide security up to a certain level. Then again, there is an adversary who is able to overcome this countermeasure and protection and again break the system. But then the question is whether this new adversary model under which the adversary is able to break the implementation is a reasonable model or not. No? Whether the adversary has those equipments and time and, let's say, facilities to conduct the attack or not. If we consider only the theory, there is no device to say that it's absolutely secure against any kind of attacks. No? Then usually by these countermeasures that we will learn roughly at the second half of the lecture, the countermeasures, they just make the attacks harder. Means that they do not provide security against all kind of attacks. Then we have to classify the attacks into different groups and different categories and say, okay, this countermeasure is able to provide the security against these kind of attacks and the other countermeasure against these kind of attacks and so on. No? And if you have one countermeasure, definitely there are some other attack vectors which are possible on that implementation. Good. The cost of the attack compared to timing attacks that you usually need to build just a counter might be sometimes also expensive because you need a very fast counter, a very accurate counter. But here you need definitely one oscilloscope. Yeah? The oscilloscope can be very cheap. I mean, at the range of $1,000 or to $2,000 or euros is a digital oscilloscope. We will talk about the oscilloscope and necessary equipments. And it can go up to 30, 50,000, and there are also oscilloscopes in the market which cost more than 300,000 euros, depending on the specification of the oscilloscope. But usually for us, depending on the implementation, if the implementation has a very high amount of power consumption and the power consumption is highly dependent on the data that it processes, means that the leakage or power consumption leakage is very high, then normal and cheap oscilloscopes are enough. But in some other cases, if the devices are new, for example, if you have a new mobile phone with a new technology of, let's say, 6 nanometer technology, the amount of power consumption is very, very small and the clock is very fast, then you need sophisticated setup and devices. Then probably this 2,000 euro oscilloscope is not enough. And 2,000 euro or 1,000 euro oscilloscope is not the limit. Means that you may also perform the attack with cheaper facilities. For example, there is something which is called chip whisperer, and then you can, which is a combination of FPGA and ADC. ADC is analog to digital converter. Actually, the oscilloscopes, digital oscilloscopes, are nothing else than this. There is a machine, there is an acquisition device inside the oscilloscope, and there is a very good low noise ADC, analog to digital converter, and then a very fast memory. I mean, if you remember, we talked about SRAM and DRAM. DRAM is a slow, and then if you want to measure the sample points with the ADC very, very fast at the, for example, speed of 10 giga sample per second, then you can never store it in a DRAM. Then you have to do a lot of fancy things like interleaving and many different modules to be able to store them in memory. For that reason, the oscilloscopes which have high sampling memory, they are also very expensive because they should be actually the SRAM, and SRAM is expensive. And this chip whisperer, as I explained, is much cheaper than 1,500 euros. But it's of course very low sampling rate. I mean, we'll talk about the sampling rate and so on later. But in some devices, you are able to perform the attack using chip whisperer, not necessarily using a 2,000 euro oscilloscope. Good. Before going to the part which we learn how to measure power consumption, we need to review power consumption characteristics of CMOS circuits. I think you have learned something about CMOS during your first years of bachelor studies, but we have to review them. The majority of today's hardware are built based on CMOS technology. I mean, most of the, for example, the CPU of your mobile phone, of your laptop, almost everything is in the CMOS technology. And this is the abbreviation of complementary metal oxide semiconductor. And there is a reason for that. There is a reason that the CMOS is so widespread, and most of the devices are based on CMOS technology. One of the reasons is immunity in presence of noise. What does it mean? First of all, in logic circuits, we show the logical values by the level of the voltage. For example, we say VDD. If you remember in the first session, I explained the VDD of, for example, 65 nanometer technology is 1.2 volt. Then around 1.2 volt is considered as logical value 1, and something around 0 volt is considered as a logical value of 0. But then how about something in between? 0.5 or 0.7 or 0.8, whether this is considered as 1 or 0. And then the gates, logical gates which work in this domain, I mean, for example, AND gate, OR gate, XOR gate, they receive the level of the voltage as the input, and then they produce the output also as a level of voltage. For example, if you have AND gate with both 0, means that the voltages are close to 0, then the output should be also close to 0, not something higher or closer to 0.3 and so on. Then it means that if you build a circuit with a lot of gates, still, if noise is coming to the system and the output is not exactly 0 volt, for example, it's 0.3 volt, it is still considered 0 and the circuit works correctly. Or if the level of the voltage should be 1.2 volt, but it's not 1.2, it's around 1 volt, it means that you have a lot of noise in your system, then still it's considered as logical value of 1, and then the system works correctly. Then the immunity in presence of noise is important. It means that if you have the CMOS device close to another device which produces a lot of noise in industrial, for example, environment, or in the airplane, still they work correctly because the environment is super noisy, but it works very well. And it has a very low static power consumption. We'll review this static power consumption in the next couple of slides. What is the static power consumption? It means that if the device does not work at all, I mean, it doesn't have any activity, then the power consumption is lower. For example, if you do not use your mobile phone, your laptop, then the battery will not be consumed much. But if you use it, then the battery is used. Yeah? It's very, let's say, logical for you now, but let's say 30 years ago, it was not like this. Yeah? Then the CMOS technology was not so widespread, and then there was other technologies like TTL, and then even in the completely ideally state of the circuit consumes some energy. It means that even you don't use your mobile phone or laptop, still power was consumed, and if you had a battery, the battery was over very early. When the static power consumption is low, the main power consumption of CMOS circuits comes from the dynamic part. The dynamic part means that when the gates are changing, when the output of the gate is changes. Yeah? We will see this. And this is the fact that we call it information leakage, means that when the circuit actually consumes some energy, means that something changed in the circuit. Yeah? And then by observing this dynamic power consumption, you should be able to understand that something changed in the circuit. Yeah? Means that you observe the activity of the circuit by observing the dynamic power consumption. Now, if we want to understand better why this is the case, why information leakage or information actually leaked through the dynamic power consumption of CMOS circuits, then we review a CMOS gate. Here we have a CMOS gate. You see that, or you learned before that this is the VDD. For example, as I said, for example, 1.2 volt, and this is the ground. And then you have a network here, pull-up network, and you have a network here, pull-down network. And the pull-down and pull-up network are connected together, and then the output of the gate is built, Q. And you see the A gate has two inputs, A and B. A is connected to these transistors, and A is also connected to these transistors, A and B, and so on. And this is explained in the slide that there are two networks, pull-down and pull-up. And what is important, the pull-up part or pull-up network is made by PMOS transistors. You see this symbol? This is a PMOS transistor, and this is an NMOS transistor. And the pull-down network is actually built by the NMOS transistors, but there is a reason for that. If you see here, Q, which is the output of the gate, will be either connected to VDD or will be connected to the ground. And you should see these transistors as such as some switches. Means that the Q will be connected to these transistors. I mean, through these transistors, those switches to 0 means that it should have a 0 value, or 0 volt, or close to 0 volt, or it should be connected to VDD through these switches. That they are PMOS. And then it should be close to VDD when it's connected through the pull-up network to the VDD. Why we have PMOS transistors here and NMOS transistors here? Because when Q wants to be connected to VDD, it should actually have a voltage close to the VDD. Means that the voltage should not drop. If it's 1.2, it should be also close to 1.2. It should not be decreased. It should not be, for example, in 1 volt instead of 1.2. And this is actually done by the PMOS transistors. Means that PMOS transistors are good to pass high values. I mean, this is the abstract representation. I mean, we don't want to get very much deep into electronics. You can just say that PMOS transistors can nicely pass high value, or high voltage, and NMOS transistors can nicely pass low voltages. Then, if Q should be 0, then it will be connected through the ground by the NMOS transistors, or it will be connected to VDD through the PMOS transistors. And if you mix them, if you use PMOS instead of the NMOS, then as I said, the output, the voltage level of the Q will not be exactly as you want. I mean, if it should be 0, it's not 0 volt, it will be, for example, 0.3 volt. Or if it should be 1.2 volt close to VDD, the voltage is smaller than the VDD. Then you should never use, or PMOS transistors are never used in the pull down, and NMOS transistors are never used in the pull up. What is important? The network should be made in a way that at each time instance, when the inputs are stable, only one network is active. It means that either this is active, passing Q to ground, or the pull-up network is active, Q is connected to VDD, not both of them. Yeah? If both of them are connected, what happens? Yeah? There is a short circuit. The VDD will be connected to the ground. Yeah? Then the circuit does not work. Good. What is this gate? Can anyone say that? What is the logical function of this gate? Then we make a table and we say A, B, and Q. Yeah, and then 0, 0, 1, 1, 0, 1, 0, 1. Okay, when both of them are 0, A and B, this one, what happens? When A is 0, this switch is off. Then, of course, the pull-down network will be disconnected. But the PMOS transistors are the way around. Yeah? Means that when the input is 0, they are conducting. They are conducting. The VDD passes through both of them to Q, means that Q will be connected to VDD. Then we have 1. When A is 1, then this is conducting, but B is 0. Yeah? B is 0, here 1, 0. This is 1, this is 0, means this is conducting, this is not conducting, then pull-down network anyway, again, is disconnected. But again, one of them is 0, B is 0. Then this is conducting, then Q is connected to VDD. Then we have 1. Here in the next one, when A is 0 and B is 1 is the same. But when both of them are 1, then these two are disconnected. And these two are connecting, both of them in series. And then Q will be connected to ground, then we have 0. What is this gate? NAND gate. Yeah? This is a NAND gate. But how do you build the NOR gate then? Okay, that was NAND, yeah, which was something like this. And this was VDD. A. Yeah, and this was Q. That was NAND. How do you build NOR? Then for NOR, yeah, then it will be all the way around. Means that A and B, which are series here, will be in parallel, and these which are actually in parallel, they will be in series. Yeah? Then we will have something like this. A, B connected to ground, and then here VDD, here A, and here B. And this is the output, this will be NOR. Good. How do you make AND? If you want to build the AND based on the NAND, how do you build the inverter? Then you build the inverter like this. Just 2 transistors. Yeah, they are connected together like this. The output of the NAND is connected. NAND is here. The output of the NAND is connected to the input of the inverter. And here is the Q bar, let's say. And this is and this point was not. Yeah? And the same for NOR. If you want to build OR, then you have to put the NOR and an inverter. The problem is that you don't have any chance to build such gates, CMOS gates, for example, AND gate, by one stage. You know? Always the delay and the size of a NAND gate is smaller than the delay and the size of an AND gate. The same for NOR and OR. XOR gates are completely different. They are much larger, but usually there is no difference between XOR and XNOR. The size and the delay of XOR and XNOR are roughly the same. No? Good, that was a bit digital circuit design. Now, we look at the power consumption of this. For example, we say, what is the static power consumption? The problem is that the CMOS circuits, or let's say these NMOS transistors and PMOS transistors, are not perfectly blocking the current. Yeah? Now, look at here again. Suppose that A and B are both 0. Yeah? Let's suppose that this is 0 and this is 0. Then this is not passing and this is not passing, and means that the guy actually current is passing through here, through the pull-up network to the Q. But these NMOS transistors, which are connected to A and B, yeah, they receive as the input 0, or let's say in transistor gate is 0, gate of the transistor is 0, and it should not be conducting, it should be blocking, but they are not fully blocking, means that there is a small current passing through this and another small current passing through this. Very, very little. Yeah. For that reason, if you do not, for example, use any device, use your device, which is CMOS, and just leave it there, and with the battery, after a couple of days, the battery will be over, because there is a small current passing through this. Even if the circuit is completely idly, it doesn't have any activity or not, but it's very, very small compared to dynamic power. And the same for the PMOS transistors. No? The same for the PMOS transistors. If they are not conducting, there is also a still current passing through them, and then anyway, there is a small current passing through the VDD to the ground. Of course, it's not a short circuit, but it's a very, very small current. This is a static power consumption, or in electronics, it's also called leakage current. When the technology becomes smaller, now if you have, as I said, I explained, 65 nanometer, 14 nanometer technology, and then 28 nanometer, 16 nanometer, 9 nanometer, 6 nanometer, and so on. When the technology scales and gets smaller, yeah, the amount of static power consumption becomes a bit higher. It's not dramatic. It's not something that say the static power consumption is now 10 times larger. It's not like this, but it became larger and larger. The problem is that these pull-up and pull-up networks have different leakage currents now. And then what we have a data-dependent static power consumption. To explain what the data-dependent static power consumption, then I have to draw again for you. We consider the NAND gate that we have seen together, right? Which was something like this. Now let's consider A equals 0 and B equals 0. What happens again, as I already draw, these two guys, the PMOS transistors, are conducting. Yeah, and then these two transistors are not conducting, but as we said, there is a small current passing through them. Yeah. Now consider that A equals 0 and B equals 1, then the shape will be something like this. And the other one actually is completely disconnected. This is disconnected, this transistor. And then again, A, there is a small current. There is a small current passing through the NMOS transistor, and then B is conducting. And now consider that A equals 1 and B equals 1. Then you have VDD, and there is a small current passing through both transistors, the NMOS transistors, and then these are both conducting. Yeah, you need to model this. Yeah, based on resistance means that there is between VDD and ground, there is nothing here. There's a wire, but there are two actually resistors here. If you want to model it, then it will be from VDD just line and one resistor and another resistor and to VDD. And here we will have the line and one resistor here and nothing. And here you have two resistors which are in series and then the line here. Of course, the resistors are different. For example, this is R of A, R of B, and here is R of A, and here is the R of A of, let's say, PMOS, and here R of PMOS of B. We can say this is NMOS, this is NMOS, this is NMOS, and these transistors are different. Then depending on the value of A and B, the amount of current which passes from VDD to ground will be different. And if you are able to measure this amount of energy or current which passes through the transistor, you see these differences based on the values of A and B. Of course, we might not be able to see or recover exact value of A and B, but if we just see the difference, that's enough to perform an attack. Yeah? Then we see that in different cases, in different situations for A and B, the amount of current which passes through the transistor, through the gate or through the circuit is different, depending on the value of A and B. Yeah? Then for this, we call and we say that the amount of static power consumption of the circuit depends on the data, or is data dependent the static power consumption. Good news for you, we do not deal with data dependent static power consumption in this lecture. Yeah? This is a line of research that I followed during the last 10 years. And there are, of course, if you are interested, there are a lot of papers to read, but we do mainly focus on the dynamic power consumption in the lecture. What is it then, dynamic power? Dynamic power consumption comes from two facts. Short circuit current. We consider the same thing, the AND gate. And we say this is again VDD. And here again the PMOS transistors A and B, and the NMOS transistors B and A. Suppose that A equals 0, B equals 1, suppose that. Then what is the situation? When A is 0 and B is 1, then definitely this pull up, VDD, the current passes through the VDD, and here the output, which is Q, let's say here we call it Q, then Q will be what? Q will be 1. Now, and this pull down transistor is of course turned off. Now suppose that A changes to 1. No? Then B stays as 1 and A changes to 1. What happens? Then the pull-up network, which was conducting through this transistor, it will be turned off, and this pull-down network, which is now connected to B and A, which both of them are 1 now, they will be conducting, and the Q will be connected to the ground. It means that Q changes from 1 to 0. The problem is that these switches through the transistors, A and B, these PMOS transistors and NMOS transistors, these PMOS and NMOS transistors, they are not ideal switches. As we said, they have some leakage current, but they also are not super fast. They are not atomic. It means that in one instance, in one, let's say, femtosecond, picosecond, they do not change their state. It takes some time. It means that the pull-up network should be turned off, which was turned on, and now the pull-down network, which was off, should be on. Then imagine that, okay, one of them is closed, the other one is open, and it should be other way around. but in the middle, when they change, in the middle for a very short time, both of them are conducting, but not fully, not with full power, but there will be some current through this change passing through this to the ground, but for a very, very short time. And the dynamic power consumption, part of the dynamic power consumption comes from this. We do not deal with this, but VLSI, very large scale integrated circuits, and the VLSI engineers are able to actually minimize this by changing the threshold voltage. Because, I mean, you probably have not learned this. Every of these transistors has a threshold voltage. I mean, PMOS transistors have their own threshold voltage. NMOS transistors have also their own threshold voltage. And then you might be able, by changing the type of a transistors, to minimize this short circuit current. And also other way around, means that if now again A changes to 0, then Q also changes to 1. Again, this happens, means that the one of them was off, the other one is on, and then the situation should be completely different. And then for a very, very short time, both pull up and pull down network are active for a very short time, which is called short circuit current. If you consider here and look at here, we have the power consumption when the output changes. But if the output doesn't change, but the input changes, for example, A is 0, B is also 0, but then A changes to 1. In both cases, the Q actually was 1 and it stays 1. Then there is no short circuit current. Of course, A changed, and of course A comes from somewhere, and it may have some effects here, but we ignore it here. So the effect is super, super small. But of course, A comes from another gate, and if the output of that gate changes, it has its own contribution to the amount of power consumption. But this gate, since the output does not change, then it doesn't have any power or dynamic power consumption or switching power consumption. Good. Another type of power consumption, which is also important, which also originate from changing the output, is that these CMOS gates, they have some form of capacitor at the output. I mean, these capacitors are not built by the engineers. They are actually built by itself. I mean, we do not intentionally build these capacitors, but in the semiconductor, when you build the gates, some form of capacitors are built. And then when Q changes from 1 to 0, if you look at here, 1 to 0 during this time, the Q was 1, means that this capacitor was fully charged. It should be discharged. What does it mean? If you have a capacitor which is fully charged, and if you want to discharging, means that the Q is now connected from VDD to ground, and this capacitor was fully charged. Now it means that actually you connect both sides or both pins of the capacitor together, means that you discharge the capacitor entirely. Then what happens? You dissipate the amount of energy which is inside the capacitor as heat. Because the energy which is stored there will be gone. By how? By turning to heat. And this is the reason when your device works, it gets hot. If there was no capacitor or no capacitor which is charged and discharged, there was no reason to become hot. But now if the output changes from 0 to 1, this capacitor was fully discharged. Now it should be charged, means that the current passes from the VDD to the ground here till this capacitor is charged after switching. After the Q is 1, or during the time that the Q changes from 0 to 1, at this time, then this capacitor also charged, and then there is another extra current coming from VDD to ground through the capacitor. And this is called actually charging power consumption. What is important, if we look at the amount of current which passes from VDD to the ground, when the output changes, from 0 to 1 and from 1 to 0, in both cases, we have short circuit current. It doesn't matter, the output changes from 1 to 0 or 0 to 1. But the other way around, when we consider the charging current, it only happens when we have the change at the output of the gate from 0 to 1. Only in this case we have, let's say, charging power consumption or charging current which is passing from VDD to the ground. In the other one, 1 to 0, the current was here, you just connected together and no current is actually passing through here. I mean, everything which was here should be just dissipated as heat. In summary, we say this, that we have charging current and short circuit current. And short circuit current is data dependent when the output changes, doesn't matter from 0 to 1 or 1 to 0. And charging current actually is also data dependent, part of the dynamic power consumption, but only if the output changes from low to high, from 0 to 1, not other way around. But we just model it in a more simple way or simpler way. We say what? We say that the dynamic power consumption is data dependent. That's all. This is what you have to learn. That if the device has some activities, if the output of the gate changes, then there is an amount of power consumption. Now let's look at an example. For example, we have an inverter. You remember now, I draw an inverter. You have just one PMOS circuit, PMOS transistor at the top, one NMOS transistor at the bottom. And then if you look at here, this is the voltage and this is the current. And here input, let's call it A, and the output Q. This is the VDD, and this is the PMOS, this is the NMOS, and this is the ground. They are connected together, and this is A, and this is Q. And this is an old technology, and you see the VDD is 3.5 or 3.3 volt, depending on technology, but this is a super old technology. And this is a simulation, of course, and then input is 0, and of course the output is 1, as you see. And then input changes from 0 to 1, of course not super fast. And the output also changes from 1 to 0 and other way around. When the input changes from 1 to 0, the output changes from 0 to 1. But if you look at the current, what is the current? Current passing through the VDD. I mean, you measure the amount of current at this stage, how much current passes through, or how much current passes through here. If you measure this current, you see that it has a jump, and it has also a jump when the output changes. But if you look at it carefully, you see that here is higher. Why? Because the output changes from 0 to 1, means that here you have the short circuit current, also the charging current, but this is not the case here. This is only the short circuit current. This is explained here, but there are many other parameters which affect the power of a CMOS circuit or CMOS gate. But at the moment in this lecture, we ignore it. The amount of electrical engineering that you have seen here is enough. And for power analysis attacks, we just take the most significant part, which is the dynamic power consumption, and we say just the power consumption depends on the data which is processed. That's all. But now, what you have seen, that was just a single gate. How about the larger circuit? Because of course what we build, cryptographic devices are pretty complex, and when you build them, there are many gates which are involved in your circuit. And the power consumption of combinational circuit is clear, right? I mean, this is a combination of the gates only, not, for example, the registers, not the memory elements, just the AND or XOR gates, the fundamental gates. And then the power consumption of combinational circuit depends strongly on some other points, and one of them is glitches. What is a glitch? Suppose you have a circuit like this. This is an inverter, and this is a NAND gate. And look at here, A and B, here timing diagram, both of them are 0. And both of them at the same time change to 1. Look at here, if both of them are 0, the input of the NAND gate is 0, then the output is definitely 1. And if you look at the output is 1, right? And if both of them are 1, also C will be 0 because this is 1. And 0 makes the output 1, then D should be also 1, which is actually 1. Yeah? But if you look at it carefully, you see there is a transient time that the output is not valid, yeah, for a short time. And this time depends on what? Depends on the delay of these gates. Because the gates that we have, I mean, we build the CMOS circuits, I mean, the circuits with the CMOS gates, they are not atomic gates. They have some delay, you know, in the range of nanosecond, picosecond, femtosecond, depending on technology. And then when the input changes, the output does not change immediately, or the output is not valid immediately. I talked to you in the first session about the critical path delay, if you remember. This is exactly this. The delay of the gates are connected together, and then you should wait enough till the output of the combinational circuit is valid, then you can store it in the register. And this defines the critical path delay and the maximum clock frequency of your circuit. And if you want to follow this, you can see that, okay, C has a delay. For example, it's called delay or time or propagation time of the inverter. You see the inverter has the input 0, and then the input changes at this point in time to 1. And then it takes some time, the propagation time or propagation delay on inverter, till the output becomes valid. But now the NAND gate has also a delay. A NAND gate had the input A changed directly at this time, and then it has some propagation time, propagation delay, which is due to the change of the A, but C did not change, C changed actually here. Then afterwards, there is another propagation delay of the gate because C changed, and then this makes the output directly 0, and then again this makes the output 1. Means that in both cases 0, 0 and 1, 1 for A and B, the output should be 1, which is actually true, but for a very short period of time, which again depends on the technology and depends on the, or depending on the size of the delay of the gates, it will be in the picosecond, for example. And this is one glitch. Yeah? This is one glitch, and what you have learned, you just learned that there is a dynamic power consumption in CMOS circuits. When the output of the gate changes, there is a power consumption. Yeah? Then for each of these changes at the output of the gates, or every gate that you have, there is a power consumption, there is a dynamic power consumption, there is a dynamic power consumption, and so on. And then the glitches are main source of power consumption in CMOS circuits. And this is not easily avoidable. Yeah? You cannot easily build circuits that they don't have any glitches. And the glitches happen in the circuit. Of course, you may be able to reduce it by some ad hoc and also some systematic ways, but you cannot build something which is completely glitch-free. Yeah? I mean, glitch-free circuits are completely different. I mean, there are some glitch-free circuits, but they are a different topic that we will deal with them later, I think, in, let's say, in the 10th or 11th session of the lecture. Now, that was just AND and OR, or AND, NAND, and inverter. Just imagine this box, AESS box. And do you know how many gates are involved when you want to build an AESS box? Around 500, for example, depending on the library that you use. Then you synthesize the AESS box. Then imagine that the input of this box changes from one value to another value, then how many glitches happen inside the circuit, and each of them leads to power consumption. And the glitches are not only ones, yeah? I mean, if you have a combinational circuit with, let's say, a logical depth of 10 gates, then you may have, I don't know, 40, 50, 100 of these changes inside this internal signals till it gets stable. Then there are a lot of glitches and changes inside the circuit. For that reason, something which is written in the DPA book, I mean the book that I explained to you in the first session as one of the main material of the lecture, Glitches in CMOS circuits are data dependent and have a strong impact on the dynamic power consumption. Of course, we do not model the glitches, but what we say that the input of the combinational circuit changes, then the amount of power consumption depends on the input. Why? Any input that you have to the combinational circuit leads to a different form of glitches. Yeah, you have a combinational circuit, and then it has an input X, couple of, for example, n bit, and then Y output, which is another number of bits. Then X changes to X prime. For every X and X prime, then there are different kind of and different number of glitches happening inside this combinational circuit. And then each of them has as we learned, the glitches have or require some energy, and they lead to power consumption or energy consumption. And then if X changes to X prime, then you have amount of power consumption. If X changes to X double prime, when X prime and double prime are not the same, then what happens? Then the amount of power consumption, amount of glitches which are available there, or due to this change, are different to each other, and then the amount of power consumption will be different. What we say then in short, in abstract way, we say that the amount of power consumption of the circuit depends on the data that the circuit processes. Now, how do we measure this? We learned that the power consumption of CMOS circuits depend on the data that they process, but how do we measure them? We need to insert a small resistor into the ground or VDD pad. I will explain this or draw it in more detail, and measure the voltage drop across the resistor. The voltage drop is proportional to the power consumption of the device. This is our chip. And then what you learned, there is a VDD line and there is a ground line. What we can do, we can put a resistor here and then measure the voltage V of R, and let's call this V of chip. When the VDD is fixed, and then when you measure VR, when the current which is passing through this guy changes, when the I is different, the same I is actually passing here as well. And what you learned before in physics, that V equals what? Ri. When the R is fixed, for example, how large should be this resistor? Depending on the technology, super old technology, you put 1 ohm. In a newer technology, you put 0.1 ohm. And then you are interested in I, then you measure V, and since R is fixed, then V is proportional to I. What is important that you should also consider and keep in your mind, for power analysis attacks, we are not interested in the amount of voltage or current in ampere, nanoampere, femtoampere, something. No, just the value which is proportional to the current or proportional to the power consumption of a device. Now, these attacks are called power analysis attacks. We are not measuring power, we are measuring actually the current. Or we do not want to get something like joule or watt or anything, related to power or energy, nothing at all, just something proportional. Now we measure the voltage using an oscilloscope, we will see later. And the current which is passing through this, we will have something relevant to this guy. Alternatively, we can put this resistor at the top. This is the VDD. This is the VDD, and we put a resistor here. This is the ground. Now this will be V of chip, and this will be the V of R. But here in this case, because one side of the VR was connected to the ground, then there is no problem. Usually the devices that we have, the oscilloscope, yeah, this is a screen of the oscilloscope, and there are some lines. Every of these connectors of the oscilloscope means one of them, you connect it here to the oscilloscope, one side to the VR, and you know these cables of the oscilloscope should be shielded, yeah, means should be connected to ground, the body of the cable. And the ground means that this should have a ground. One of them actually connects to here, means that the ground or shield of this, and the other one is connected to the other side of the resistor. That means that there are two lines. And the ground of the oscilloscope is also connected to the earth. The ground of the device is also connected to the earth. Means that, yeah, the ground of both are connected together, no problem. But if you want to measure here, you see none of them is actually ground. Yeah? Then you cannot connect it to the oscilloscope unless the ground of this guy, ground of the chip, is completely floating, is not connected to the earth, which is not recommended. Yeah? When you want to measure something, it's recommended that to connect the ground of all devices together. Then you cannot connect these two to the oscilloscope if the earth of them or ground of them are the same. Then you need another device in between, which is called the differential probe. Means that you connect this then later easily to here, and this differential probe measures the difference between the voltage of these 2 points. We will get back to this, but this is a differential probe, one example of a differential probe. Or what you can do, you can measure the current via a current probe. Yeah? We will see this. I will explain this later in the next slide. What is this current probe and why it can be used. Or alternatively, if you cannot measure the power, you can measure the electromagnetic radiation, or EM. Yeah? Electromagnetic radiation or electromagnetic field of the chip means that the chip is there, it works. Yeah? You don't measure the power consumption, you do not change the PCB to put the resistor anywhere. You put just a probe at the top of the chip. Then it measures the radiation of the chip, which is proportional also to the power consumption. You will see some examples and get a better idea. And they are, for example, the probes. And the other side of the probe, they will be connected to some amplifiers, and the amplifier is connected to the oscilloscope. This is also the things that I explained, but in more detail. Yeah? We put the resistor at the top. Usually this is our choice. Yeah? I will explain you why. This is our actually favorite case, that you put the resistor at the VDD line instead of the ground line. Why? Because in some devices, particularly in new technologies, there is a VDD, which is, for example, 1.2 volt, no, for the technologies that I explained, 65 nanometer. But then the I/O voltage is different. I/O voltage means that in which voltage level this chip is communicating with another chip. There are different technologies. Super old technology is 5 volt, means that the communication between chips were 5, means that zero value was close to 0 volt and logical value 1 was close to 5 volt. It became to 3.3 volt afterwards, and then to 2.5 volt, and then afterwards to 1.8 volt. Yeah, they are let's say, standards. And below that, we don't go for the I/O because it has a high effect on the noise, and then it might be noisy, and then the devices cannot communicate with each other easily. Then for that reason, the chips, usually the devices, have different VDDs. One is the VDD of core, which is, depending on technology, 1.2, for example. And then there are other VDDs, like the VDD I/O. Depending again on the standard, it might be 2.5 volt, it might be 3.3 volt, it might be 1.8 volt. And then if you put the resistor at the ground pad here, you not only observe the activities of the chip due to the core, you also see all the currents passing through the ground because of the I/O activities. Meaning that it communicates through the I/O, and you see all this noise in your power consumption, power measurements. Then our wish or favorite is to put this resistor at the VDD of the core, that one which is responsible for the power of the core inside, not of the I/O, and then measure it. As I explained, what you can do, you can use a differential probe here. But differential probe is an active component. If you see, it should be also connected to the power supply. There is a power supply, VCC, of the power supply of the differential probe. And this, because an active element, an active component, it adds noise to your measurement by itself. It means that this is there, you can use it, but it's not recommended. And of course, it measures the difference voltage between here VDD, two sides of the resistor, and then you see something like this, the voltages. Another way, which is actually also a favorite, is to measure these two sides, directly the chip, not the resistor. But what is important, what you see here, this is in AC mode. Why? The previous one was in the DC mode. I don't know whether you learned this before. I guess not. The measuring in DC and AC mode. When you measure in the DC mode or DC coupling by the oscilloscopes, you exactly see as a voltage what comes to the probe. If I draw the same thing, this is the chip, and this is the VDD and the resistor, and here the ground. What we said, we want to measure these two. It means that we connect these to our oscilloscope. Okay, imagine this is our oscilloscope. If we measure in the DC mode, voltage, then it will be close to 1.2 volt if VDD is, imagine that this is also 1.2 volt. And then the variations, there will be some variations, because of the power consumption, there will be some variations. And then your oscilloscope should be very good. Oscilloscope means that should have some features, means that you should zoom in that area. And for example, measure this area with very high accuracy. And these variations are super, super small, in the range of, for example, 10 millivolt. Then not every oscilloscope can do it. And because of this high DC shift, you bring it up here and then measure, then it will be also noisy. Then what we do, you probably have not learned it during your study because you are computer science students. If you have studied electrical engineering, definitely you know it. Then we use actually in the AC mode or AC coupling, you have high pass filter. High pass filter means that this variation in the AC mode comes close to 0. It will be here. And then you are able to easily enlarge it, scale up, and get something like this with high accuracy. This is the reason that when you connect the oscilloscope to the chip like this, two sides of the chip instead of two sides of the resistor, then you need to measure in the AC mode. Otherwise, you will have very much noise and the accuracy will be very small, and your oscilloscope may not actually support this, because it should be supported that you have a very high DC shift if the amplitude of your signal is very small. Or if the signal is very small, if I explained before, I mean, you remember this, as explained, the AC coupling or AC mode is actually a high pass filter. And DC blocker, you can sort of use some form of DC blocker, and DC blocker is just a high pass filter. And it removes the DC shift, brings the signal close to zero. Then you see the changes. And then you can also amplify it and then see a very good signal. And then there are some examples for the amplifier. And this is a DC blocker, this is one amplifier, and this is another amplifier that you can use here. Now, the current probe. If you look at here, the resistor is completely gone. We cut this and then bring the VDD to the coil, to the current probe. You see here there is a hole inside the current probe. Then the cable of the power should pass through this hole. It goes through this hole and it's connected to here. Of course, it might be noisy because of this. And then again, every changes, because there is a coil here, and the coil converts the changes in the current through the field, because it changes actually to the electromagnetic field, and electromagnetic field is changed to the voltage, and then you can easily measure it by the oscilloscope again in the DC mode. In the DC mode. And this is one photo of picture of the current probe, which is available in the market.
When we measure the voltage over the chip instead of the resistor that we put at the beginning of, like after the VDD, why can we still assume that this is proportional to the current, because the resistance of the chip isn't necessarily, sorry, not about this slide or 2 slides before, when we just measure the simple setup where we just measure the...
Because the voltage, we said the current passes through here. And then instead of measuring the voltage over the resistor, we measure the voltage over the chip. And the sum of them should be actually constant. Sum of this plus this should be VDD. And if you measure one of them, and then you say the VDD of the chip, VDD should be the same as V of chip plus V of resistor. And the sum of them are constant. Either you measure this one or you measure this one, which is proportional to the current. Good. That was the current probe and all of them together in one picture. But you see, you have to change the PCB. PCB is clear, printed circuit board. And then you have to find this VDD, and it's not always easy because the chip usually doesn't have a single VDD line. There are multiple VDD lines that they are connected internally inside the circuit, but there are multiple pins, and you should provide the VDD to all pins. I mean, when somebody designs a PCB, then you have to find out which pins are the VDD and then modify the PCB in a way that the resistor is placed in an appropriate way to be able to run the attack like this. Then it might be hard, in some cases even not possible, because the PCB has a couple of layers. And then the solution, if you do not have any option to put the resistor there, then you put an EM probe, electromagnetic probe, on the top of the chip, or close to the capacitors which are responsible to the VDD of the chip, and then you see somehow similar effect. Now some photos and pictures of the EM probes. First of all, you should learn something about the packaging of the devices. They are different FPGAs from different families and different technologies. First of all, this chip is already decapped, means that the upper side of the chip is completely removed. And then what you see here, actually this is the chip, and this is the package. But the chip, the pads of the chip should be connected to the pins of the package. And pins of the package are there, and then there should be some small wires that they connect the pads of the chip to the pads of the package. And they are called bonding wires, bonding wires. And this process is also called bonding. And there are devices, sometimes manual, sometimes semi-automated, sometimes fully automated. And in electrical engineering department here in TU Darmstadt, definitely there are fancy bonding machines in different groups. And this is one technology, that you have the chip which is fabricated. This is the semiconductor, but then because it's super tiny and this example is super large. I mean, the chips that, for example, I design in my group, they are 1 millimeter by 1 millimeter, that size. But at every side, at every millimeter, 1 millimeter, we have 12 pins to be connected. And then there should be bonding wires that they connect this to the package, which package is, of course, much larger, let's say 3 centimeter by 3 centimeter. This is the size. This is one technology by the bonding wires. Then what you can do, you can, of course, put the EM probe at the top of this chip. But if you remove the package and you are closer to the chip, you get better signal, of course, because again, a bit of electronics. Activity inside the chip will make a field, electromagnetic field. And then when you want to measure the electromagnetic field, you should be close to the field. If you're far from the field, once you get a distance from the field, then the amount of energy that you observe with your EM probe, electromagnetic probe, becomes smaller and smaller and smaller. They should be closer to the field. And then sometimes you need to decap it, sometimes with some acid. There are some other fancy devices to remove the package, because usually they are plastic packages, means that they will be completely filled by plastic. Sometimes no, there is a cap at the top. This was a bonding technology, and another one is flip chip. Flip chip means that something like this, there is no bonding wire at all. This is the back side of the silicon, of the semiconductor. This is the front side. This is the back side. Means that the package is designed like this. This is the package. This is much larger than the semiconductor. The semiconductor is designed. The pads are there, and then the chip is actually flipped over the package and is glued on the package. There is no bonding wire, no soldering, nothing. And then this package has pins at the bottom, and the pins of the bottom, of course, there are different technologies, size and type of the pins of the package. We don't deal with the package now. And sometimes there is a flip chip, something like this, but there is a cover, metal cover over the chip. If you want to put an EM probe on the top of the chip, there are different ways. For example, you put just a large EM probe here. This is a super large EM probe at the chip, and then you need to change the position because it's super large. You can find it manually which position is the best. Sometimes it's large here. I mean, you can see this is roughly the same package type. This is the flip chip, and there is no metal cover. Or you put it again on the plastic package, not a problem. But then if you want to put the EM probe at the top of this chip, with the metal cover, you have to remove the metal cover. For example, this is one example. The metal cover is removed, then you have access to the silicon here, and then put the EM probe. But these EM probes are super large, and then they see the activity of the chip, which is somehow close to power consumption, particularly if you put this probe close to the capacitors of the chip, not on the chip, and the capacitors which are on the PCB. I will talk about the capacitors a bit later, but these are not the only type of the EM probes. Some other EM probes are super tiny and small. They are localized EM probes. This photo or these photos are super enlarged. The size of this EM probe is 150 micrometer. Is the diameter of this. Means that you cannot actually manually position it. If you want to position it manually with hand, you definitely touch these bonding wires, and then they will destroy it, and then the chip will not work anymore. And you have to use some tables, XYZ tables, either manually to change it, or with some motorized tables. You change the XY position to put the probe at the top of the chip, find the location, you should go through some programs which scans the entire position of the locations of the chip and find one appropriate position to attack. By this localized EM probes, usually the attacks are stronger than the power analysis attacks because it's somehow localized. And if you find a good spot, then you have the radiation or activity of one part of the circuit instead of power consumption, which is the activity of the entire circuit. Usually what happens, the chip is designed like this, and then there are VDD lines. As I said, there are different VDD lines, yeah, I mean, and they are connected internally together. And then you want to put the resistor somewhere. First of all, there are many of them in the chip, and they are also connected to some capacitors close to the chip. There is also a VDD, then some, I mean, I don't expect you to be PCB designer, and you may not have seen any PCB design, but then it should be like this, and then they are, as I said, internally connected together and so on. Yeah, there might be more. What you have to do, and of course, wait a second, and they are also connected together, yeah, and over the PCB, and they are supplied by something which we call it the voltage regulator, yeah, voltage regulator. Sometimes it's called VRM, voltage regulator module. For example, it gives you 1.2 volt. I mean, the input, for example, is 3 volt, yeah? And some other devices close to the voltage regulator to give you a stable 1.2 volt. If you put a resistor here, if you put a resistor here, this doesn't work. No? Because VDD is also connected through other lines, yeah, through here. And then the current that you want to look is actually not passing through that resistor that you want. Then what you have to do, you have to put the resistor here. You know, that's okay, but these capacitors, what do they do? What is the purpose of them? To stable the signal. Yeah? And then what you want to see as the voltage, what we said the voltage, what you can do, you can connect the oscilloscope to the VDD and the ground of the chip. These capacitors actually make the signal that you want to see completely smooth. They kill what you want to see. And what you have to do, you have to remove them. No? You have to remove them. This is one option, to completely remove them from the PCB. Yeah? Then it would be a normal situation. But then one thing which might be problematic, if the device works at a very high frequency, these capacitors are necessary. Otherwise, the device may not work at a high frequency anymore. Then you have to keep them. Now, what you do, then you have to bring these capacitors, for example, here. Yeah? Or if you are able to do that, I mean, there are multiple ways to cut these lines, yeah, and then connect them together, and then with just one resistor connect the VDD to the VDD of the chip. What I want to say, some electrical engineering knowledge is necessary to change the PCB. Sometimes these changes are not possible at all because they are in the middle layer of the PCB. And then usually putting the electromagnetic probe at the top of the chip or close to these capacitors is the better way. Now something about a digital oscilloscope. You see two examples that I have here. One is a fancy one with a screen, and there is a PC inside, and this will be right at the moment over 50,000 euros. And there is another one which doesn't have any screen and then USB cable, that's all, and then everything should run on a PC. And this, depending, I mean, the prices went up during the last couple of years, and I don't know exactly the price of this guy at the moment, but you should be able to buy something at the range of 1 to 2,000 euros. Of course, depending on the specification. What are the important things? Bandwidth of the oscilloscope. Yeah, you should know that the signals, I mean, they have a frequency, and then what is the bandwidth with the maximum frequency that the oscilloscope is able to see the signal. You know, because if the signal has a higher frequency components, then the oscilloscope, for example, is able to measure at most with 300 megahertz. Yeah, I mean this bandwidth is not related to the clock frequency. Yeah, I mean, again, this is a bit electrical engineering. This is the bandwidth of the signal, how fast the signal actually changes. Yeah, the power consumption signal that you want to measure. And what is important, we need in most cases something between 20 megahertz, which is super low bandwidth. I mean, every cheap oscilloscope that you buy actually has the higher bandwidth than 20 megahertz, and up to 1 gigahertz or even to 4 gigahertz you may go. Yeah? But why? Low bandwidth for power consumption. Why? Again, remember that we had a resistor on the PCB, and the capacitors are removed, and the probe, and so on, and DC and AC coupling, and so on. Everything that you have in the measurement setup, you know, of the power consumption measurements is a low pass filter. The resistor, which is called also shunt resistor, which is placed on the PCB itself, the package of the device itself, they are low pass filter. It means that they filter the signal that you want to see. Then if you measure this signal, which is already filtered, low pass filtered, by one oscilloscope, which actually has the bandwidth of 1 gigahertz, you do not gain much. Now, even in power consumption measurements, because you have some noise, you can actually turn on the low pass filter, internal low pass filter of the oscilloscope. For example, these oscilloscopes have some low pass filter, not digital one, the analog one, that you can turn on to 20 megahertz. And it doesn't matter if your oscilloscope supports up to 1 gigahertz or not. 20 megahertz is enough, you know, for power measurements, usually. And for EM measurements, the situation is different. If the power consumption signal is something like this, for example, is something like this, every clock cycle we will see, then the EM signal, if you at the same time measure the EM signal, it will be something like this. Yeah? And this actually exactly tells you that the bandwidth of the signal. Yeah? And then for EM measurements, you need oscilloscopes with higher bandwidth. Yeah? And if you connect a 20 megahertz oscilloscope to an EM probe, everything is actually filtered and you barely see anything. Then another one is a sampling rate, because we are dealing with the digital oscilloscopes. Something like 1 mega sample per second or 500 kilo sample per second, depending on the bandwidth, depending on the clock frequency of a device that you want to measure. And up to 10 giga sample per second are enough. Again, 10 giga sample per second for EM measurements, and low sampling rate for the power measurements. Yeah? And sampling rate is clear, means that how many points are sampled per second, you know, the speed. And another one is a sampling memory. I explained this for you, yeah, that they are based on usually SRAM. Yeah, and if you go for 10 giga sample per second, and then usually the oscilloscope that you buy with that price, 50,000, the memory is, yeah, at the moment, what you look at the market, oscilloscope with 10 giga sample per second usually has 256 megabytes of memory. Yeah, just 256 mega, not giga, yeah, mega. And if you want to upgrade it to something with, let's say, double or 1 gigabyte, then you have to pay around 20,000 euros just for the memory. because it should store all these samples with data speed. Yeah, and of course the SRAM with data speed does not exist. Then they have to use a lot of modules with a small delay and interleave the data which are saved into the memory. Then another one is the quantization accuracy. What is a quantization? We are dealing with analog signal. Yeah? And what is the ADC? Changing or converting the analog data to digital data. And for example, this is the full screen of your oscilloscope, for example, and then from here to here will be quantized. For example, if you have 8-bit ADC, then it will be quantized to 256 cases. Yeah? Then if these are two different cases, something in between does not exist. No? Then this is a quantization. And usually digital oscilloscopes have 8-bit ADC, and 8-bit ADC or 8-bit accuracy is actually enough for us. Means that, as I said, you need to bring this signal of full of your screen of your oscilloscope. Otherwise, if you just feel a small part, means the quantization is very low. Yeah, because you use, for example, just 4 bits of the ADC if it's just a small part of your screen in the oscilloscope. Yeah, you should try to cover the entire screen or use the maximum accuracy of your oscilloscope. Nowadays, there are 12-bit oscilloscope on the market. It's called HD oscilloscopes. But for our purposes, usually 8-bit is enough. Yeah, we do not really need 12-bit oscilloscopes. I already explained, yeah, if you have unprotected device, no countermeasure at all, the small oscilloscopes and a small setup should be enough. If it's highly sophisticated device to perform the attack or target, then you also need highly sophisticated setup to perform the attack. Now, what is the process? Yeah, the procedure to measure power consumption to be able to then perform the attack. We learn the attacks later. Yeah? In your setup, you have different kind of components. Power supply. Yeah, this was for example, the voltage regulator, as I explained. Measurement circuit like this shunt resistor, the probe or EM probe, and then digital oscilloscope that you have. You have a PC, but nowadays digital oscilloscopes have a PC by themselves. I mean, these fancy ones, I mean, these can be both one device. But if it's a USB oscilloscope, then you also need a PC. And this is your target device, cryptographic device. And sometimes there's a clock generator, which most of the time is internal. You know, I mean, internally clock is provided. Or if it's external, then the clock is also provided by another facility. Or sometimes it's inside the PCB and you do not actually control it. But this is in general, all components which are available there. Then some of them, as I said, they are combined. Then the procedure is like this. Of course, the device is supplied with the power and the clock signal. You know, you turn everything on clearly. And then the PC configures and arms the oscilloscope. What is important, I mean, what you have not learned, I guess, is arming the oscilloscope. These oscilloscopes, they are super fast. For example, with 10 gigasample per second, and the memory is small, let's say 8 megabyte or 16 megabyte, then they are measuring all the time and they are not saving everything in the sampling memory, you know, because they cannot in a real time transfer all data to the PC or anywhere. Suppose at 10 gigasample per second, they are produced and each sample is just 1 byte. There's 10 gigabyte of data per second. Yeah? How do you want to analyze them? How do you want to save them? Yeah? How do you want to transfer them? Then oscilloscopes are working like this, that you need to trigger them. There is another signal, which comes from, for example, cryptographic device and says, okay, for example, I start the encryption. For example, when you communicate with the cryptographic device, you give the plaintext and then you say start. And then the encryption function looks at the start and then starts encrypting the given plaintext. Yeah? This start signal is something that you should use for the oscilloscope. Say, okay, at the same time, it should also start measuring or start collecting the data, because oscilloscope is always measuring, is always turning the analog data to digital data, but it's not saving into the sampling memory. You know? Then you should say oscilloscope, okay, now start. But you should also configure the oscilloscope and say, hey, this is my trigger signal. You know, for the oscilloscopes, they call trigger. This is my trigger signal. But then be ready if one low to high signal comes to the trigger signal, then I start measuring or I start saving. And this process to watch this trigger signal is called arming the oscilloscope. Yeah? Then you arm the oscilloscope, because at the middle of the time, the oscilloscope may, this signal that you use for the trigger may also have some changes. Then you don't want the oscilloscope to measure or collect or change the sampling memory. Then at one specific time, you say, hey, arm the oscilloscope be armed. When the oscilloscope say, I'm armed, then you send the data to the cryptographic device. Yeah, PC sends command and start execution of the cryptographic device. At the same time, then automatically the oscilloscope will be triggered. Yeah, the oscilloscope will be triggered and records the power consumption, or EM, measurements of the cryptographic device, and the PC receives the output of the cryptographic algorithm. You know, for example, this is AES. It sends the plain text, now it receives the ciphertext, or it doesn't know the plain text, it just says a start, and it receives the output, or something like this. Yeah, I mean, not necessarily you always have the plain text or ciphertext. Sometimes only plain text, sometimes only ciphertext. Yeah, if you don't have any of them, the attack will be a bit hard. Yeah, if you don't know the plain text, neither plain text nor the ciphertext, most of the attacks will not work unless the cryptographic device, for example, works in a counter mode, and you can guess what is the input, for example, or part of the input. And then also PC receives a recorded power trace from the oscilloscope, and then I store them in the file or somewhere, and then you repeat this process from the step 2 to 6 as many times as you want. No? This might be super slow depending on the architecture, depending on the way that you measure, and so on. Yeah? But in the lecture, we do not deal that much about the measurement facility and measurement setup and how to speed it up and so on. Good. You have seen some power traces before in the first assignment. Yeah? And this is one, for example, to show you and give you some ideas. And as you learn today, dynamic power consumption are the measure or the most important part of the power consumption of CMOS circuits. And then what you see here, these peaks, actually they indicate one clock cycle, because at every clock cycle, something changes inside the circuit, and then the power is consumed, and the next clock cycle, and the next clock cycle. Now, what is important is that, for example, your circuit works at the positive edge of the clock. Now, then the positive edge of the clock, you have peaks, but you have also some peaks in the power consumption traces when the clock changes from high to low. Of course, there are some devices that they work at the positive and also at the negative edge of the clock. But just imagine that your circuit works at the positive edge. Then if you look at the power consumption traces, it will be something like this. At the negative edge, there is also a peak, which is usually data independent. Now you see these are small ones. Why do we have some form of power consumption at the negative edge of the clock when the state of the circuit does not change? There are two reasons for that. One is that the flip-flops or registers inside the circuit, they have to change the state, the situation in the flip-flop that, okay, there was a high to low of the clock because the clock are connected to all flip-flops, and then there are small changes inside the flip-flop. Of course, the content of the flip-flop does not change, but it's a state changes. Yeah, because it should understand, okay, the clock was high and then now low, and then the next low to high I have to save. Yeah, then the state of the flip-flop should change internally. Then there are some changes inside the flip-flop because of the high to low, and at the same time something which is called clock tree. What is clock tree? The clock that you provide to the circuit cannot be connected to all flip-flops of your circuit. For example, you have 1,000 registers inside your circuit. Now, there is something which is called fan-out. Now, fan-out, the number of signals that you get from one gate or one signal, you cannot connect one signal to 1,000 registers. Otherwise, this will be super slow. Every change that you want to have will be super slow. Then what you have to do, the clock will be connected to one buffer or clock buffer, and then this will be connected to a set of other buffers depending on the fan-out and depending on the specification. And then these guys, each of them again, to another buffers and so on. And then you connect these output of the buffers to the registers. Now, for example, again, from each of them, you get 8 fan-outs, and each one supports 8 flip-flops. Now, and then you have to get output from this tree at the same level. Yeah, all of the registers should be supplied from the same level or depth of the clock tree. Otherwise, there will be a race. Means that some flip-flops get triggered earlier than the other flip-flops, and the circuit does not necessarily work correctly. Yeah? This is called a race issue, race problem. Now, what are these buffers? How do you build the buffers? The buffer is only built by 2 inverters. Now, of course, you can make it better and say this is inverted and these are also inverted. Yeah, and then just make sure the number of inverters which are in the clock buffer or clock tree, they are, for example, even. Yeah, then make sure that the signal is not negated. Then what you learned? You learned about the glitches. You learned about the changes. When the clock changes from here 1 to 0, from 1 to 0, then these are also changing. Then they consume energy. Although the circuit does not do anything, you have clock buffers. Not only the flip-flop, also the clock buffer, and then you see something like this. You see these guys. But they are usually what? They are data independent if the circuit does not have any activity in the negative edge of the clock. Because there are circuits that they work at both edges of the clock. Now you can look at the power consumption trace and see, the device was idly, but now it does something. And you see here that it's increasing. Yeah? And if you look carefully here, there is a high peak, low peak, high peak, low peak, high peak, low peak. There is a low peak in between. And this is exactly this negative edge of the clock. And then afterwards, the device does not work at all. I mean, it stopped completely, but still you see some small things. What are they? Again, data inactivity, but there's a clock tree, there's a flip-flop. Huh? Good. What are the quality of the measurements? I mean, we have to consider that there are some noise into our measurements, because what we do, what you have seen, there's a low pass filter, high pass filter, and then there are a lot of sources of the current which we measure, and then the signal that we get from the oscilloscope, which is the analog to digital converter, is not as stable. Means that it's not constant. Means that if you repeat the same measurement with the same input, with the same data, and the state of the circuit is exactly the same, you do not get the same signal. There will be small changes in the signal. No? And these are due to 2 facts. One of them is electrical noise. If you as I said, repeat one measurement several times with a constant input and output, the resulting power traces are not the same. One of the reasons is noise of the power supply. You remember the voltage regulators? The voltage regulators have some also noise. Depending on the type of the voltage regulators, then you have a different amount of noise in your measurements. And if the clock is also provided externally, the clock generator has also some noise. If it's internally, it may also have some kind of noise. If you have EM measurements, there are radiation from the other devices which are close to your device. For example, if you remember, I talked about the static and dynamic RAM. The dynamic RAM, one of the things that I did not explain to you, the dynamic RAMs should be refreshed, which is actually not done by you, by the controller of the DRAM. Why? Because the values which are stored in the DRAM, there are actually some capacitors, tiny capacitors, and over the time, they will be discharged, and the value that you store in the memory is gone. Then there should be a mechanism to update the value or refresh the values which are the DRAM. And this is activity. And if you put the EM measurements, and then you have a DRAM, then you see all these refreshing activities over the DRAM, and you have a lot of noise in your measurements. And the quantization noise is something else. I mean, we explained, even if the signals are super nice, if they go a bit higher and lower, then they drop into the next level of the quantization or the higher level of the quantization. Because as what I explained, if you have 8-bit of ADC, then there are 256 cases or levels that you can quantify. Then it may change from one level to another level, even if there is not much electrical noise into analog signal. Another type of a noise, you should learn these two things carefully because we deal with them next week. The switching noise is, the effect of switching noise is similar to the electronical noise, but the origin is different. We refer to variation of power traces that they are caused by cells that are not relevant for the attack. You may say the noise of the power consumption is also not relevant to our attacks, but they are originating from the device that you want to perform the attack, but they are not considered in your attack. For example, the bandwidth of your measurements and the clock frequency, they may completely change the situation. They may also, I mean, depending on the definition, the bandwidth and the noise originating from the bandwidth and also the clock frequency may also fit into electrical noise. We will see later in more detail. But what is important that you consider the noise of the core processor, for example, when the ALU is targeted. When you want to perform the attack on one part of your circuit, you will see this later. For example, you are interested in just what we learned in the timing attacks on the MSB of the SPOX output, for example. You want to just make the attack, but we will learn later that what is the dependency of the power consumption to the MSB of one of the SPOX output, but the SPOX has other outputs as well, and each of them also affect the amount of power consumption. And if you do not consider them in your attack, the effect of, or their effect is considered as the switching noise in your measurements. Means that what we want to exploit is a small part of the power consumption, but this is added with many other things that they are not relevant for our attack. What is the effect of the clock frequency on power consumption traces? If the clock frequency is 2 megahertz, this is one example, that you see the power traces for every clock cycle, and this guy is the negative edge of the clock, and you see this bump, and this is because of the low pass filter, which slowly changes, goes up and down and so on. Because as I said, the power consumption traces are low pass filtered. And if you increase the clock frequency to 10 megahertz, you see these peaks are getting closer together to each other. Just keep in your mind that the x-axis is different. Here you have from here to here 1.5 microsecond. Here the scale, of course, is different because it's 5 times faster. The clock is 5 times faster. Still, you are able to recognize the positive edge and the negative edge of the clock. You increase it to 20 megahertz. you see almost no negative edge, because again, it's low pass filtered. And if you increase it to, for example, 60 megahertz, the device works fine. I mean, depending on the device, and this device works fine at 60 megahertz, but you don't see anything basically with respect to the clock. Everything is overlapped to each other. If you measure the electromagnetic radiation, you usually see every clock cycle, even at the 60 megahertz, depending, of course, on the bandwidth of your oscilloscope. Here is the bandwidth important. If, again, your bandwidth of your oscilloscope is, for example, 20 megahertz, and even if you measure EM traces or you have EM measurements, again, something similar will happen if your oscilloscope doesn't have enough bandwidth. What is important, the clock frequency is not exactly the same as the bandwidth of the power consumption traces. They have an effect on the frequency of the power consumption traces, but it's not like this, that if you have clock of 60 megahertz, then your oscilloscope is 120 megahertz bandwidth, then I should be able to see everything. You may think it's like this, but as I said, this is a power measurement. It's not this filtering is not only for the oscilloscope, as for the packaging and the shunt resistor and the entire power consumption measurements. They build a low pass filter. Even if you use an oscilloscope with 1 gigahertz bandwidth and you measure power consumption traces, you still see something like this. What I said is that if you now measure EM instead of the power consumption, and then the clock frequency is 60 megahertz, you should be able to see the clock cycles if your oscilloscope has enough bandwidth. But here, if your oscilloscope even has 1 gigahertz bandwidth, the power consumption traces will be overlapped. It's the packaging, the shunt resistor, and the probes that you have. All of them entirely build a low pass filter together. And as I say, the PCB itself, the wires in the PCB, they build a low pass filter for you unintentionally. And then they filter the signal. And even if your oscilloscope has a higher bandwidth, you do not see much with respect to the clock cycles if you measure power consumption. If you're an attacker, you may decrease the clock frequency. It means that if you have that control, if you have that ability, it's recommended to decrease the clock in a way that the power consumption of adjacent clocks, they do not overlap, because if they overlap, the attack still will be possible here, but with more noise. It means that more traces you need, because it's actually, again, kind of a noise that, as I explained, this is a kind of a switching noise which comes to your measurements. Now, we are getting to the end of the slide or end of this session. These things that I explained here might be not relevant anymore, but you should actually know the history. The topic of the power analysis attacks is roughly 25-year-old. And that time, 20 years ago, it was not easy to collect and store very large amount of data, because the data power consumption traces were very long, and it was not easy to store them, and process them, and not only storing, the processing. And then I remember that the evaluation labs, or still there are evaluation labs that they fill 1 hard drive every week. And then they have to actually collect this data, and store them because they are evaluation labs. They have to keep all this information for a couple of years. Of course, cloud is one option, but sometimes they are not allowed to share this data with anybody or third parties, and they have to locally store them. And then again, we store the power consumption traces. We have to analyze them using some servers, and then if they are stored in a cloud somewhere else, and then you have to, every time you want to run the attack, you have to read terabyte of data from one server to another server. It takes some time. Then many years ago, that was some discussions how we can compress this data, the power consumption traces, because as I explained, the power consumption values are already low pass filtered. And then usually the peak of the power consumption of every clock is important. It means that if you just do the peak extraction, you extract the peak, you see a maximum extraction or peak extraction, then you should be able to actually still run the attack. But the shape of the attack, the curves that you get for the attacks are not that nice, but still they are possible. Or you get integration over every clock cycle, means that you have to cut the traces into cycles, clock cycles, and then integration, or sum them up, sum up the values, or sum the absolute value of each clock cycle, or sum of the squares of each clock cycle. Different things have been used, but as I said, I just showed you this because you should know the history, but nowadays nobody does it, nowadays everybody just saves the data. We have multiple terabytes of space and also servers that they can process all of this. And then compression of the power traces is not a large issue at the moment. Taxonomy of power analysis attacks. I mean, this is something that we make ourselves busy during the next weeks. There are different types of power analysis attacks. We categorize them based on two properties. One of them is with characterization and without characterization. What is the characterization? When I want to perform an attack on a device, if I have a chance to look at another device which is similar to the target device, and then learn something from that device by setting the key by myself, by knowing the all intermediate values, this is called an attack with characterization. It means that I want to perform the attack on device X, which is a microcontroller with one, for example, microcontroller with one program. I go to the market, I buy the same device, same microcontroller, same PCB if possible, and then I do not run my own attack on the X device, but first I try to have the same program on the device which is called Y device, the device number 2, or Y, device Y. And then I try to understand and learn what is the relation between the power consumption or such information of the device when I can control everything, when I can control the key, when I know the plaintext, when I know the intermediate values, and so on. Once I learn this, which is also called profiling attacks, with characterization, or let's say profiling attacks, then with this knowledge, I come to the target device and try to perform the attack on the target device. With all the knowledge that I got from another device, which is similar to the target device, while I could control all its intermediate values. And another property of the attack is either we are able to measure as many as traces that we want, or no, we are restricted to a very low number of traces. For example, if a device is used in a scenario when there is a session key, and the key is changing, for example, every 10 seconds, and you are not able to collect more than 100 traces from for one key. In the attacks with the characterization, as I explained, the attack consists of two phases. The power consumption or saturation and leakages of the attack device should be categorized. They will deal with this later. The mean and the variance of the processing of different data values are determined. This is something that we will learn, and we call it template attacks, for example. And then the attack on the target device using the knowledge from the first step. And the attacks without characterization, the attacker does not have any knowledge about the power consumption characteristics. The attacker may know the design architecture, the attacker may know the program which is running on a microcontroller, but they are not the characterization attacks. In the characterization attacks or profiling attacks, you should do exact the same attack, or let's say collect the power consumption, collect saturation and leakages from a device which is similar to your target device. Knowing some information about the design architecture is not considered as profiling attacks or attacks with characterization. Now we categorize them in 4 cases or 4 categories. If you have no characterization, there is no way to do characterization, and then you are bonded to a few number of traces, the attack is called simple power analysis, or SPA. And if you do not have any limit, then the attack is called DPA. This is a general form, DPA, but is not related definitely to a particular attack, which is called differential power analysis. We will see many different kind of these attacks, not only DPA, but in literature sometimes this category of the attacks, non-profile attacks without any limit on the number of traces, sometimes they are referred to just DPA. And then if you have the option to characterize or profiling attack, then it's called template-based SPA and also template-based DPA. In the template-based DPA, the number of traces will be very small, but in the template-based SPA, the idea is to actually ideally just recover the secret with only one power measurement. This is the ideal case. And of course, for that, by recovering the target with one single power trace, then you need definitely profiling. You need to learn and understand what is the behavior of the circuit or what is the physical characteristics of the circuit for different data which it processes. SPA attacks are an important class of attacks, usually for public key crypto. We will see this in next session. And DP attacks are usually for the symmetric block ciphers. Now, as I said, we will see them in detail from the next week.